Hello everyone. In this video, I will talk about symbolic computation using Python. We will go over the package SymPy, and with this package, we can do all sorts of computations symbolically. And SymPy can simplify expressions, compute derivatives, take integrals and limits. We can solve equations and work with matrices. Many other operations and problems can also be solved using this package symbolically. It includes modules for plotting and printing as well, and it can also generate us some latex code if we want to use equations in an article or report. So let's see some basic examples. So I have some example code here. First of all, we need to after we do the installation, we need to import. So we are using this SymPy package. And if you want to import all the functions and classes from this package, you can simply use this code in line 10. Now, we need to define symbolic expressions because this package is all about symbolic computing. So we can, for example, create a symbolic expression x plus 2y. And in order to do that, first we need to declare the symbols that we will be using, such as x and y in this equation. So as you see, we create this x and y variables symbolically. And then we can use it to write our expression. And then if you like, for example, we can print it on the screen to verify. So let me just comment out this part and then go step by step. Now I just have this simple example here and I want to run the code. So the code here, once we run this code, basically we can see the expression x plus 2 times y. And if you want, you can also print out the type just to verify. And you can see that we have the variable type as a symbolic expression. Now basically note that we wrote this x plus 2 times y just as we would if x and y were ordinary Python variables. But in this case, instead of evaluating to something, the expression remains as just this expression. That's the difference in symbolic computing. I mean, in the usual case, we will be just evaluating when we declare some variables, we will be assigning some numerical values, etc., or do some operations. But here, it just remains as a symbolic expression. So this is quite different from our regular numerical evaluations with the Python variables. And we can see some other operations with an expression. For example, if we add 1 to our expression, which is x plus 2y, then it will still be a symbolic expression. Or you can subtract x, and if we subtract x, only 2 times y remains. So let's see the result. The print statement, the first one we added 1. The second one we actually subtracted this x. Basically we have 2 times y remaining here. Now let's go over a few more examples. And in this part, now we have an example on actually pretty print. In order to create a nice print, we can use this additional feature of this package. And then basically we see an example here that will take the derivative of an expression. And here we have actually two functions multiplied, the sine function times the exponential function, and we put an x here to indicate that we want to differentiate this expression with respect to x. And what would we see? I mean, what's the derivative of these two expressions multiplied? Remember, in calculus, we know the product rule. The product rule, basically, you take the derivative of, for example, let's start with the exponential. The derivative is itself. So you have sine exponential and then plus a cosine term times the exponential. So we know how to take the derivative, but this can be done here symbolically, and you see that this is the result for the derivative. You can consider other operations such as taking an integral. For example, here we have a simple example. We have again this expression, which is the derivative we calculated in the previous statement. And if we take the integral, we will get back sine times the exponential. So let's see. And as you see, this is the result of the integral here. Let's look at one more integration. Here we want to take the integral of sine x squared, and basically you can see the domain is from minus infinity to infinity. So that's the domain we are interested in. And simply if we evaluate, as you see the last print statement here, the square root of 2 times square root of pi over 2. This is the result of the integration. And as you notice, this is the analytical result because we are using the symbolic computing here. We are not doing the numerical integration here. Here's a limit, taking a limit example. Let's say you want to take the limit of this expression, sine x divided by x, and the limit is as x approaches to 0. So what's going to be the limit? Basically, it will give us 1. Another example here, suppose we want to solve an equation. As you see, if my equation is just a simple one, x squared minus 2, and I want to solve it, so my equation is basically x squared minus 2 equals to 0. So if you try to solve it, you will, of course, get x equals to square root of 2, right? We know how to do that on a piece of paper, but Python will do it for us. And as you see, the roots are plus or minus square root of 2. And as you see, we can do more operations. One more example here that you can use in solving a differential equation. Again, this is very useful for us since we know how to solve the differential equations, but this package can do it for us, or we can verify our result to double check. And the equation we want to solve is a second order ODE, where you see this second derivative of y minus y equals to the exponential t. So our function is defined with respect to this variable, the symbolic variable y. Okay, so first we define it, and then we need to use the solver for differential equations. So we need to specify the equation because we are saying solve this, but it needs to recognize solve which equation. And here we input the equation. So we have the derivative, the second derivative of y minus y, and the right hand side of this equation is exponential t. And we need to tell that solve this equation with respect to the y of t. So we specified everything that is required. So we specified everything required here, and then final outcome we will print it on the screen. And if we run the last statement, as you see, this is the solution of this ODE, second order ODE. And note that you have two arbitrary constants, C1 and C2. As you do the analytical solution, basically of a second order ODE, you will get two constants, two arbitrary constants. And here it is denoted as usual as a C1 and C2. So final example is for calculating an eigenvalue of a matrix. And in basically matrix algebra, suppose we are given a 2 by 2 or 3 by 3 matrix, and you want to calculate the eigenvalues. We know that we need to solve the characteristic equation, and we can do it analytically, I mean, for many simple matrices. But here, again, this package can do everything for us. We need to input the matrix, and the matrix is the first row is 1 and 2, and the second row is 2 and 2. So basically, we input these row by row, and then use this eigenvalue method that will basically print out the final eigenvalues for this matrix. And as we see here, the eigenvalues turn out to be 3 over 2 minus the square root of 17 divided by 2. So this, we have a minus, and then we have a plus version of this. And finally, we can conclude this code with a LaTeX translation of the symbolic expression. For example, here we have the cosine square, and I want to integrate this function over the domain of x from 0 to pi. So it will give me a symbolic expression, but I want to be able to use this result in my, let's say, LaTeX report or my article, etc. So this function in that sense is very useful if it will convert the last expression into a LaTeX code, as you see here, and you can copy paste this to your LaTeX code, and that will save your time. So these examples are, I think, simple but very useful, and you can use this package on many different types of problems, as we have seen some of them in this part. Next, we will continue with some more examples now, using, let's say, the other important operation, which is the Laplace transform. And we have talked about this, or you might already know, the Laplace transform is also a useful technique for solving the differential equations. And here first we are actually importing all the necessary, methods from our package, including Laplace transform and the other mathematical functions such as sine, cosine, exponential, Heaviside functions. These are necessary in the next examples. But first, let's start by defining the variables. For a Laplace transform, we would need the time variable represented by t, and then we have the Laplace domain variable, which we will often represent by s. And let's look at a few examples. The first example, I want to take the Laplace transform of this expression e to the power minus a times t. So we declare this as an expression, and then This Laplace transform function requires, first of all, an expression, because we will integrate this with respect to this expression. We will integrate actually by inputting this expression. And then we will need to have the symbolic variables for the time variable and for the Laplace domain variable. And here we are using these symbolic variables already declared and defined here. So this will output us the result of the Laplace transform. And then the second and third examples are actually also quite similar. The only difference is now we are considering alternative functional forms, such as the sine function. If you take the Laplace transform of this function, again, you need to input this as an expression and input your symbolic variables in this Laplace transform, which is the time domain and the Laplace domain variable s. And similarly, of course, one can consider the cosine function as well and evaluate what's the Laplace transform of the cosine function. And here is the answer actually. I mean, you can alternatively do this on a piece of paper to double check. Just write down the cosine of t and then evaluate the integral for the Laplace transform. And basically, we can compare our handwritten analytical result with the symbolic computing analytical result obtained from Python. And then you have the Heaviside here. And then we have the Heaviside function, but the procedure is pretty much the same. We still need to define the expression for whatever function we are interested, and then basically input this function and the appropriate variables, and then the result will basically give us the Laplace transform. And as you see, all these examples are very similar, like with different functions, like this one here, t times e to the power minus 2 times t. This is just an alternative expression just in case you want to calculate the Laplace transform of this function. Then you can use the appropriate code here. So let me run these the Laplace file. Okay, so if we run this, we can see basically the Laplace transform for this variable e to the power minus 2t, that is given by this expression here, as you see, s plus 2 to the power minus 2. Now, the final two examples here, suppose I want to evaluate my Laplace transform result for a particular s value. Let's say s equals to 2. Then how do I evaluate this transform for this particular value? Well, what you need to do is actually nothing complex. Once you apply the Laplace transform, the next thing is to use the subs method with the 0th element, and you will assign this s equals to 2. Alternatively, here you have another example with the cosine function. And for the cosine function, again, I want to, let's say, evaluate the Laplace transform for s equals to 1. This is going to be s equals to 1. So in order to evaluate the result, you can use this subs method and just evaluate whatever Laplace transform that you get. Now, finally, there is one more file here that we can just take a look at these examples. In this file, again, we have defined some symbolic variables, and this time we have hyperbolic, the hyperbolic sine and cosine functions. So we declare these functions, and then, as usual, suppose you want to calculate the Laplace transform. And if you want to calculate this, basically you need to input your function that is defined, and you should also input the time variable t and the domain variable s. And suppose I take only the transform. So let me just run this part, and then we can print out, let's say, the hyperbolic sine, and let's print out the cosine that we applied Laplace transform. And for the moment, just comment this for a while. So let's run it. So as we see, we just extract the Laplace transform itself. So I just put a 0 here. Then it just returns me the Laplace transform. But if I don't put this, let's do it one more time. Okay, so as you see, if I don't put this 0, it will display these 3 elements, which also shows basically this if s equals to 1, actually the denominator is 0, so we have some discontinuity there. So for other values, no problem to evaluate the Laplace transform. So as you see, we can obtain the Laplace transform for all these functions relatively easily. Well, if you want to do some plotting, etc., then we can construct a linear space and evaluate the functions for plotting here. So you can see that if I uncomment this part of the code, it creates me some linear space, and then I can evaluate the sine hyperbolic function at these time discretizations. Okay, so basically from 0 to 5, I can partition into 500 equal length intervals. Okay, and then at these values we can evaluate the sine hyperbolic and cosine hyperbolic functions. Optionally, I mean, if we want to plot, basically we can create a plot of these functions here, and I'm going to be we are actually plotting the original hyperbolic sine and cosine functions. So as you see, we can also put some text to indicate what is the Laplace transform of this sine hyperbolic function. And similarly, actually you can print the Laplace transform for the cosine hyperbolic functions. And basically you can present this sine and cosine hyperbolic values evaluated on our linear equally distant space. So finally, if we run this whole code, the last part will produce us these charts. And as you see, we have the sine hyperbolic and cosine hyperbolic functions that are plotted for the domain from 0 to 5. If you just go back to the code, we actually define this interval from 0 to 5 on our linear grid. and evaluated these hyperbolic functions over these domain of values. And furthermore, the Laplace transform values are also just displayed as a text box. So basically, these are the examples that should be useful for general purpose, and obviously many other examples can be considered, but these are the pretty much fundamental types of functions, especially for many different operations such as differentiation, integration, solving equations, or even taking the Laplace transform will be really easy if you use the SymPy package. Thank you for watching.